We're gonna go on a journey, starting with that feeling of pure panic and ending up in the world of super precise modern medicine. Yep, today we're talking all about adrenaline and some of the other master molecules inside our bodies.
You totally know that feeling, right? Your heart just starts pounding, your palms get all sweaty, maybe you just swerved to miss something in the road or you're about to step on stage. Your whole body just kicks into high gear. So what's really going on in there? What's pulling the levers? Well, it's not magic. It's some seriously cool chemistry.
So that incredible full body reaction, what we call the adrenaline rush or fight or flight, well, it's all run by this very special family of chemicals. It's time to meet the molecules in charge. And here's the official name for them, the catecholamines. Now, what's so wild about these guys is that they're double agents. They play two roles. On one hand, they act as hormones, which means they travel all through your bloodstream to send messages to distant parts of the body. But then, they also act as neurotransmitters, zapping super fast signals directly between your nerve cells. It's a 1-2 punch of communication.
Okay, I know what you're thinking, a chemical structure. But don't click away, I promise, this is simple. Look at it, it's really just built from two pieces. You've got this ring structure called a catechol ring, and then this little tail called an ethylamine tail. That's it. This simple little blueprint is the foundation for all the amazing molecules we're about to meet.
All right, so now that we know the basic recipe, let's meet the three big players in this family. You'll see that each one is just a small twist on that same blueprint, but man, do they have wildly different jobs. First up, dopamine. Yeah, you've probably heard of this one. It gets called the pleasure molecule a lot, but that's kind of selling it short. It's really the motivation molecule. It's what drives you to get things done, what helps you focus, and it even has a say in how your heart contracts. And if you look at the structure, you can see it's the simplest one of the bunch.
Okay, next we have norepinephrine. This is the mobilizer. Think of it as your body's internal alarm system. It's the one that screams, "Attention!" It gets you ready for action, makes you more vigilant, and one of its biggest jobs is to squeeze your blood vessels to keep your blood pressure up when things get intense. And last but not least, the star of our show, epinephrine. You probably know it by its more famous name, adrenaline. This is the first responder, the emergency supercharger. When the situation is critical, this is the molecule that floods your system, jacks up your heart rate, throws open your airways, and basically prepares you to either fight like crazy or run like the wind. So where do these incredible things even come from? I mean, your body doesn't just have a giant tank of adrenaline sitting around. No, it's way smarter than that. It builds them on demand in this super efficient little chemical factory. Let's go take a peek at the assembly line. Okay, this diagram looks a little busy, but it's basically a recipe. And it all starts with one simple ingredient we get from our food, an amino acid called L-tyrosine. From that one starting material, your body's enzymes go to work, step by step, turning it into something called dopa, and then into our big three, dopamine, norepinephrine, and finally, epinephrine. It's a beautiful, elegant process. Let's just break it down real quick. Step 1, an enzyme snips at tyrosine, and boom, you get dopa. Step 2, another enzyme makes a tiny change, and now you've got dopamine. Step 3, a different modification turns that dopamine into norepinephrine. And for the grand finale, deep in your adrenal gland, one last little tweak turns that into epinephrine. Just a perfect 4-step chemical cascade. All right, so our factory has built these powerful little messengers. Now what? How do they actually, deliver the message? A molecule floating around is pretty useless unless it has somewhere to land and something to talk to. And that something is a receptor. The easiest way to picture this whole thing is with a simple lock and key analogy. Think of our catecholamines, our adrenaline, our dopamine as the keys. And then all over the surface of your cells, you have these millions of tiny molecular locks. We call them receptors. When the right key finds the right lock, it fits in, turns, and that is what triggers a specific action inside the cell. Now, for adrenaline and noradrenaline, these locks come in two main flavors, alpha receptors and beta receptors. Just think of them as, two different brands of locks. They might respond to the same key, but they are absolutely built differently. And they unlock totally different doors, causing different things to happen inside our cells. And this right here is where the system gets truly brilliant. Check this out. the exact same key, epinephrine, can have completely opposite effects depending on which lock it plugs into. So when that key hits a beta-1 lock in the heart, the messages speed up, beat harder. But when that same key finds a beta-2 lock in your lungs, the messages chill out, relax, and open up so we can get more air. Then it hits an alpha-1 lock in your blood vessels and says, squeeze tight, raise the pressure. Isn't that incredible? One molecule, multiple messages. It's how the body can have such precise, fine-tuned control over everything. Okay, so this is the real game changer. Once scientists figured out this whole lock-and-key thing, an entire new world of medicine just exploded into view. Because they realized, hey, we don't have to be stuck with the body's natural keys. We can be locksmiths. We can design our own, even better keys.
See, the body's natural keys are perfect for a split-second emergency, but they make for pretty terrible medicine. For one, they're super unstable. Their effect is massive, but it's over in a flash. And you can't just take them as a pill because your stomach acid would just chew them up. So they're just not practical for long-term treatment. And here's a perfect picture of that evolution. On the left, you've got epinephrine, Mother Nature's key. And on the right, that's salbutamol. You probably know it as albuterol. It's the stuff in most asthma inhalers. I mean, look at them. They're almost identical, right? But scientists made a few very clever, very deliberate little changes to the design. And those tiny little tweaks, they change everything. So by making those tiny little changes, scientists created a much smarter designer key. This new key, salbutamol, is a master at picking the beta-2 locks in the lungs, the relax and breathe locks. But it's really clumsy and bad at fitting into the beta-1 locks in the heart, the speed up locks. And what's the result? A life-saving asthma drug that opens your airways right up without sending your heart into overdrive. It's targeted, it's precise, and it all comes from knowing how these locks and keys work. And believe me, this story is nowhere near finished. This whole idea of designing custom keys for specific molecular locks, it's one of the hottest areas in medicine right now. Right now, researchers are making keys that only target beta-3 receptors to help with things like overactive bladder. For diseases like Parkinson's, the approach is twofold. They're not just making better and more stable dopamine keys, they're also designing molecules that act like bodyguards for the dopamine you already have, protecting it from breaking down. The precision we're achieving is it's mind-blowing. So think about it. We started with a single simple amino acid, and from that one little building block, you get heart-pounding rush of fear, you get intense focus, and you get an entire universe of medicines that save lives every single day. It all boils down to the elegant chemistry of these tiny little molecules. It really makes you wonder, doesn't it? What tiny molecule is going to completely change our lives next?